A key idea in 3.3, which is actually not part of our curriculum, is how to use derivatives to help sketch graphs. So let's just walk through a quick example of how we can kind of apply all of this knowledge to creating graphs of functions. So let's just read through the strategy. Basically, it's not exactly a step-by-step process, but it's just a way of analyzing all of the components of a curve. So first step, it says, what's the derivatives and what is the domain? So it's sort of like noting what values are problems, what values don't work in the function, like is it defined at -1, is it defined at 0, so forth. But also finding the derivatives, because the derivatives, as we found, are helpful for finding mins and maxes, increasing, decreasing, concavity, inflection points. All of the curvature can be determined by calculus. So another thing it says to find is what are the critical values of the function. Because those we can then use the first and second derivative test to figure out whether those are mins and maxes. It says to figure out where it's increasing, decreasing. Where does it have extrema, again, which you can use either the first or second derivative test for. It says to find inflection points by setting the second derivative equal to 0 and using that to determine the concavity. All of those things you can kind of find at the same time. And I recommend using the second derivative test because we naturally go through the process of finding everything. And basically the last thing is sketch the graph. Use all the information to graph it. And let's just try to do this for the last example from this section. So it says, help create a graph of f of x is equal to x cubed minus 3x plus 2. It says to mark all critical points. This would be a very typical test question if I wanted you to create a graph using calculus. But basically, I would just run through the second derivative test. So first derivative here of f of this function f prime would be 3x squared. Derivative of 3x is just 3, and derivative of 2 is 0. And naturally, we could then find the critical values by setting it equal to 0. So I'll just go ahead and keep track. Critical values are determined by setting that equal to 0. So set f prime to 0. I could, again, add 3 or just factor. If I factored out 3, that would leave me with x squared minus 1. And x squared minus 1 is the difference of squares, which would factor as x plus 1 times x minus 1. And so this would give me two critical values, c is equal to 1 and c is equal to -1. Okay, cool. And basically at -1 and 1, I could then figure out, well, what is the value of those points by plugging it into the original f. So f of 1 and f of -1. Because again, I need to sketch this curve. I'm always sketching the original function. So every point, I could always just graph points as well. That's, graphing 101, plug in numbers, figure out where they are. But, we can use calculus to determine more about the shape of the curve. So for 1, that would be 1 cubed minus 3 plus 2, which actually is just 0. So f of 1 gives me a 0 value. And f of -1 would be -1 plus 3 plus 2, which would be 4. So f of -1 would be 4. And what calculus has led me to believe is that those are possibly relative mins and maxes. And again, the second derivative test would help me figure that out. So that's where I could go, well, what about the second derivative? Well, the derivative of 3x squared is 6x, and the derivative of -3 is 0. And so basically, I could figure out, well, an inflection point occurs when this is equal to 0. So I set this equal to 0, and dividing by 6 would just leave me with x equal to 0. So the inflection point would just be at 0. And if I were to plug that into the original function, f of 0 would be 0 minus 0 plus 2. I would get this particular point right here. So far I have a critical value, and an inflection point. And that is kind of like those are the important points. I always want to know where those are. And again, I figure out where they occur by using the first and second derivative respectively. And then I plug them into the original to figure out where the points are. And then last but not least, what I can probably guess is that these are connected. But at the end of the day, I could check, well, is this a min or max, and so forth. So if we were to finish with the second derivative test, so I'll just go ahead and write second d test here. Remember that the second derivative test is you take the critical values and you plug them into the second derivative. So if I do f double prime of -1, that would tell me if this is a min or max. And plugging -1 into f double prime would just be -6, and so that would be concave down. This would be a max value. So at -1, I know I'm going to have a maximum by the second derivative test. And f double prime of +1 is just going to give me 6, which would indicate a minimum, which again would be right here. So what I know is that it's going to turn around like this, and it's going to turn around like that, because at those points we have relative mins and maxes. And I can guess, that the inflection point is going to change from concave down to concave up in between. So I kind of have an idea that my curve looks something like this in between all of those points. And again, if I want more detail, then I just need to plot more points. Like if you figure out, well, what does it look like at 2? Or, of course, you could always use a graphing calculator to help you figure all this stuff out. But labeling all of this and seeing this sort of math is what I would want you to do with, and a big component of the next exam is understanding the first and second derivative tests and so forth. So you can, imagine a test question where I ask you to find the derivatives, find all this sort of information. And so what you want to be on top of is knowing, when to set it equals 0, when to plug something into where, because that can be quite challenging if you, aren't too familiar with the tests. And anyways, looking at the graph, we can kind of see a little bit further. Well, if we plugged into, excuse me, if we plug in 2 into our function, we'd get 4. We can always use a calculator to help us figure out more values of the curve, but it appears as though it's going to increase quite rapidly to the right. And if we plugged in -2, I'm going to get 0. If we plugged in -3, I'm going to get -16. And obviously you could find the intercepts. Those will also help you figure out behavior of your curve. But basically we have a general sketch of our curve, and labeling the critical values and inflection points is an important component of graphing functions, especially at the calculus level.